So what if you learned that almost everything you see in the universe began with just a single, incredibly simple element?
Literally just one proton.
Right, one proton. But it somehow manages to, light up every single star in the night sky. It creates the water we drink. And if you look at the massive global investments happening right now, it might actually hold the key to the entire future of human civilization.
Yeah, it really is the ultimate cosmic paradox. I mean, you have the absolute simplest atomic structure in reality, but it's fundamentally responsible for the most complex phenomena we know of, like biology and potentially our transition to a zero-emission economy.
Which is huge. So let's just jump straight into the deep end here for this deep dive. Because to understand why this single proton is currently the obsession of the global energy sector, we kind of have to look at how it essentially built the universe from scratch.
Right, you have to go all the way back.
Exactly. Rewind 13.8 billion years to the Big Bang. At that point, things are just way too hot and chaotic for elements to even exist right now.
Yeah, the universe was basically this superheated soup of plasma. It was just particles flying everywhere.
It was total chaos.
Total chaos. And it took about 380,000 years for that rapid expansion to cool things down enough for subatomic particles to actually settle. And when they finally did, an electron was captured by the gravitational pull of a single proton.
And that is the exact moment the very first atom formed,
Yeah.
hydrogen. Element number one.
Exactly. And because it was the first one out of the gate, and the universe was expanding so rapidly, that basic building block just got mass-produced on a scale that is honestly unimaginable.
And it still dominates everything, right?
Oh, absolutely. I mean, roughly 75% of all normal matter in the universe today is just hydrogen.
That is wild. But I want to dig into the mechanics of that for a second. Because, just having a lot of a simple gas doesn't automatically give you a glowing galaxy.
No, it doesn't.
So how does a single proton with one electron, like if we think of it as the most basic single stud Lego brick in the box, how does it actually become a cosmic engine? Like we know it's nuclear fusion, but what is the physical trigger that forces a star to actually ignite?
Well, it really comes down to a battle between gravity and electrostatic repulsion. So you have these ancient colossal clouds of hydrogen gas floating around in the early universe.
It's massive nebulas.
Right. And over millions of years, gravity just starts pulling that gas together. And as more gas clumps up, the gravity gets exponentially stronger, which just crushes the gas inward.
And obviously, as the volume decreases, the pressure and the temperature just absolutely skyrocket.
We are talking millions of degrees at the core. Now, normally, two hydrogen protons want absolutely nothing to do with each other.
Because they both have a positive charge.
Exactly, so they magnetically repel each other. But the crushing gravitational pressure of the star becomes so intense, and the kinetic energy from all that heat gets so insanely high that they actually overcome that repulsion. They literally smash into each other and fuse.
And that fusion creates a slightly heavier element, which is helium.
Yes, but the math of that fusion is where the real magic happens. Because 1 plus 1 doesn't quite equal 2 in this scenario.
Wait, what do you mean?
Well, this is the secret to the universe right here. The new helium atom that gets created actually weighs just a tiny, tiny fraction of a percent less than the original hydrogen atoms did.
Oh, right. The missing mass.
Right, the mass defect. And that missing mass doesn't just vanish into nowhere. It converts entirely into energy following Einstein's E equals mc squared.
And since the speed of light squared is a massively huge number, even a microscopic amount of missing mass just releases a catastrophic amount of energy.
Trillions of times a second, just a constant thermonuclear explosion. And that outward explosion of energy pushes back against the inward crush of gravity, which stabilizes the star. So, the light hitting your face when you walk outside, that is ancient hydrogen violently destroying itself in the core of our sun.
That is just, it's mind-blowing when you really think about it. But before we bring this all the way down to Earth, I do want to touch on the isotopes, because our sources mention that not all hydrogen is identical.
Right, there are variations.
Yeah, so the vast majority is protium, which is just the one proton we've been talking about. But you occasionally get these variations that manage to grab a neutron or two, right?
Yeah, so deuterium is the one you see most often in nature. That one has one proton and one neutron.
Okay.
It acts chemically just like normal hydrogen, but it's literally heavier.
Oh, so that's where the term heavy water comes from when it bonds with oxygen.
Exactly. But the real focus in advanced physics right now is tritium.
Tritium. That's the one with two neutrons.
Yes, one proton, two neutrons. And that specific ratio actually makes the nucleus unstable, meaning tritium is radioactive.
But that instability is actually useful for us, or?
Oh, incredibly useful. In major experimental reactors today, like the ITER project over in France, physicists are using a mix of deuterium and tritium. The extra neutrons actually lower the activation energy required to achieve fusion.
So it makes it easier to spark the reaction.
Right, it's basically how we're trying to build a miniature star right here on Earth to get clean energy.
Which perfectly sets up this kind of wild contradiction that I want to get into. We just outlined how hydrogen is this incredibly violent, explosive fuel of stars. But then how does that exact same highly combustible element become the stabilizing foundation of biological life? Like, how does star fuel become half of the recipe for the water that puts out fires?
It's all about hydrogen's absolute desperation for chemical stability.
Desperation.
Yeah, because it only has that one single electron. Its outer shell is half empty. It wants two to be stable, so it is incredibly eager to share that electron with other elements.
Okay, and when it meets oxygen, which is highly electronegative.
The oxygen atom essentially bullies the hydrogen atoms.
What bullies them?
Yeah, oxygen pulls hydrogen's shared electrons very, very close to its own nucleus. And this leaves the hydrogen protons slightly exposed, which creates a molecule that is electrically lopsided, or, polar.
Right, so it has a slight positive charge on the hydrogen side and a slight negative charge on the oxygen side.
Exactly. Which means water molecules act like tiny little magnets, constantly sticking to each other.
Ah, so that polarity is everything.
It really is. It's why water has surface tension, why it has a high boiling point compared to similar molecules, and why it can rip apart and dissolve almost any substance it encounters. I mean, it is just the perfect biochemical medium.
But the sources make this fascinating point that I feel like we often overlook. We always call ourselves carbon-based life forms, right? We treat carbon like the absolute superstar of biology.
Oh yeah, carbon gets all the PR.
Exactly. But if you actually look at the molecular structure, carbon is really just the scaffolding. Hydrogen is doing all the heavy lifting.
It is. Almost every organic molecule in your body, your fats, your proteins, your carbohydrates, it's essentially a carbon backbone that is completely coated in hydrogen atoms.
Wow.
But the most elegant example is actually your DNA. The two strands of your genetic code are held together by hydrogen bonds.
I've heard the analogy that hydrogen acts like the zipper on a DNA molecule, but how does that actually work mechanically? Like, why doesn't it just permanently glue the strands together?
Well, because a hydrogen bond isn't a true covalent bond where the electrons are perfectly, permanently shared. It's more of an electrostatic attraction.
Like the magnets again?
Right. The slight positive charge of a hydrogen atom on one side of the DNA ladder is just attracted to the slight negative charge of a nitrogen or oxygen atom on the other side.
Ah, so it's a magnetic attraction, not a structural weld.
Which is key, because it means it's strong enough to keep your genetic code perfectly stable, but it's just weak enough that an enzyme can easily break those bonds to unzip the DNA when a cell needs to divide and replicate.
That is so cool.
Yeah, if hydrogen formed permanent, hard chemical bonds there,
Ugh.
biology would just freeze in its tracks. Life couldn't exist.
So this invisible gas is literally holding our cells together. It's filling our oceans. It's powering the sun, which brings us to human history. Considering it is literally everywhere, how did it take humanity so long to even realize it existed as a distinct element?
Well, mainly because in its pure elemental form on Earth, hydrogen gas is completely colorless, odorless, and tasteless.
So it's invisible.
Totally invisible. And more importantly, it is so incredibly light that the moment it is released, it just floats up and escapes Earth's gravity entirely. You don't just, stumble across a puddle of pure hydrogen in the woods.
Right. So who finally caught it? How did we figure it out?
The major breakthrough was by Henry Cavendish back in 1766. He was this eccentric English scientist, and he was experimenting with dropping metals, like zinc, into strong acids.
As you do in the 1700s.
Right, just mixing dangerous things in a lab. And he noticed it produced a gas that bubbled up. But he didn't realize it was a fundamental element at first. He just knew that if a spark got near it, it would pop and burn.
Oh, wow.
Yeah, so he just called it flammable air.
Flammable air. That is such a great 18th century scientific term. So how do we get from flammable air to the name hydrogen?
That was Antoine Lavoisier, the French chemist. He essentially built the framework for modern chemistry. He took Cavendish's work a step further and realized that when this mysterious flammable air burned, it was actually reacting with oxygen in the atmosphere.
Okay.
And the byproduct of that combustion was pure water.
Wait, so burning it created water?
Exactly. So he took the Greek words hydro, which means water, and genes, which means creator. The water former, hydrogen.
That is a massive conceptual leap.
It really was.
But recognizing it in a lab is one thing, right? Harnessing it is another entirely. When you look at our sources on the Industrial Revolution, it really seems like our mastery of hydrogen was the only thing that allowed the human population to explode the way it did. And I'm talking specifically here about the Haber-Bosch
Oh,
process,
absolutely. Without Haber-Bosch, half the people on Earth today would literally starve.
which is a terrifying thought.
It is. The challenge back in the early 20th century was agriculture. Plants need nitrogen to grow. And the atmosphere is 78% nitrogen, but it's locked up as N2 gas, which is held together by this insanely strong triple bond.
So the plants are surrounded by it, but they can't actually use it.
Right, it's basically a chemical fortress that just refuses to react with anything.
So scientists had to figure out how to crack that fortress.
Exactly. And Fritz Haber and Carl Bosch figured out that if you subject nitrogen gas to immense heat and pressure over an iron catalyst, you can actually break that triple bond.
But you need something for the free nitrogen to instantly bond with, right?
Yeah.
It also will just reform N2.
Enter hydrogen.
There it is.
They flooded the chamber with hydrogen gas, and the nitrogen bonded with the hydrogen to create ammonia NH3. And ammonia is the direct precursor to synthetic fertilizer. We are literally using hydrogen to pull fertilizer out of thin air.
That is incredible. And from there, the industrial floodgates just totally opened. Our sources note its use in petroleum refining, right? To crack heavy crude oil and remove sulfur.
Yeah, and it's used in food processing, too, to hydrogenate liquid oils into solid fats.
Oh, right, hydrogenated oils.
We even use pure hydrogen environments in electronics manufacturing to prevent oxidation when making silicon chips.
Wow. And obviously, we cannot ignore space exploration because it's the lightest element, but it packs an enormous amount of chemical energy. Liquid hydrogen is the ultimate rocket fuel.
Yeah, NASA used it for the Apollo Saturn V rockets, the space shuttle, and now the SLS rockets for the new Artemis moon missions.
Which brings up, I think, the most notorious association people have with this gas. You mentioned using it as an aviation fuel, and a massive portion of the public immediately pictures the Hindenburg disaster in 1937.
Oh, of course.
Just a giant silver airship bursting into flames. Is that historical fear justified when we talk about, building a new hydrogen economy?
Well, I mean, the Hindenburg is burned into the public consciousness for a reason, and hydrogen is undeniably highly flammable. But modern forensic investigations into that disaster reveal a much, much more complex story than just hydrogen is dangerous.
Right, because it wasn't just the gas that was burning, was it?
No. The outer skin of the Hindenburg was a cotton fabric, and it was coated in a mixture of cellulose acetate and aluminum powder.
Wait, aluminum powder, isn't that a primary ingredient in solid rocket boosters?
Yes, it is. They essentially painted the airship in a highly flammable, thermite-like substance.
Oh my God.
Yeah, so when a static spark ignited a gas leak, the skin caught fire immediately. And here is where hydrogen's unique properties actually save lives. Because the gas is so incredibly light, the hydrogen fire burned intensely, but it burned straight up and out.
Oh, so it went away from the people.
Exactly. It escaped the passenger compartment very quickly.
Which is why the majority of the passengers and crew actually survived the crash.
Right, so the engineering lesson there wasn't to abandon hydrogen, it was to radically improve materials, science, leak detection, and containment. I mean, we handle millions of tons of industrial hydrogen safely every single year now.
Okay, so that perfectly brings us to the crux of the modern debate, the transition from industrial chemical to a global energy source. We're constantly hearing about green hydrogen as this, silver bullet for the climate crisis. But I want to push back on the enthusiasm here a bit because the thermodynamics of this whole concept seem wildly inefficient.
Okay, walk me through your concern there.
Well, currently, we don't just mine pure hydrogen, right? Most
Yeah.
of it is what's called gray hydrogen, where we use steam to rip it off of methane gas, which obviously releases massive amounts of CO2.
Right, that's gray hydrogen.
And then there's blue hydrogen, which is the same process, but you capture and store the carbon underground, which is better but still relies on fossil fuels. But to make green hydrogen the holy grail, we have to build giant electrolyzers, take clean electricity from wind or solar, use it to split water into hydrogen and oxygen, compress that hydrogen under immense pressure, transport it, and then run it through a fuel cell in a car to turn it back into electricity and water. You lose energy at every single step of that process.
You do.
So why not just take that solar energy and put it directly into a giant lithium battery? It seems so much simpler.
It is a totally valid critique, and you are completely right about the thermodynamic losses. A battery electric system is much more efficient from a pure physics standpoint,
Hmm.
but batteries have a fatal flaw,
Hmm.
which is weight and energy density.
Meaning they are just too heavy for certain jobs.
Exactly. Think about long-haul trucking or commercial aviation or maritime shipping. If you tried to power a massive oceanic cargo ship with lithium-ion batteries, the batteries would be so heavy the ship would literally sink. Hydrogen gas, or liquid hydrogen, stores significantly more energy per pound. It allows heavy transport to refuel quickly and carry heavy payloads over long distances, with the only tailpipe emission being pure water.
So the goal isn't really to replace the battery in your daily commuter car. It's meant to decarbonize the heavy industry that batteries simply can't touch, like steel manufacturing or cargo trains.
Exactly. But to do that, we face an incredible infrastructure hurdle, largely because of a phenomenon called hydrogen embrittlement.
I saw this in the sources. This is where we can't just use existing natural gas pipelines, right? What is actually happening to the metal?
So because a hydrogen atom is just a single proton and electron, is the smallest atom in the universe. If you pump high-pressure hydrogen gas through standard steel pipes, the hydrogen molecules actually dissociate on the surface of the metal into individual atoms.
Okay.
And those atoms are so microscopic, they permeate right into the crystalline lattice of the steel itself.
They just walk right through the atomic structure of the pipe.
Yes. And as they accumulate inside the metal, they recombine, build up pressure, and cause the steel to become brittle and develop microcracks. We literally have to invent and deploy entirely new metallurgical alloys and polymer coatings just to safely pipe this gas across the country.
Which explains why green hydrogen is still significantly more expensive to produce and transport than fossil fuels.
Yeah, it's a massive economics and scaling problem, intertwined with deep material science. Governments and private sectors are pouring hundreds of billions of dollars into overcoming this right now. But there is also this massive geological hunt underway for something called white hydrogen.
White hydrogen, what is that?
It's naturally occurring pockets of pure hydrogen gas trapped deep underground. It's created when water reacts with iron-rich minerals in the Earth's crust. If we can drill for pure white hydrogen the way we currently drill for oil, it completely changes the economic equation.
Wow. That would be a game changer. It is just staggering to step back and look at the sheer scope of what we've covered today.
It really is.
I mean, we tracked a single proton emerging from the cooling plasma of the Big Bang. We examined the physics of how gravity crushes those atoms to ignite the thermonuclear engines of stars. We looked at the electrostatic polarity that creates the water sustaining our lives and those weak bonds acting as the literal zipper for our DNA.
Yeah.
And then we went from 18th century scientists popping flammable air in a lab to cracking atmospheric nitrogen to feed the planet to the massive engineering hurdles of running a global zero-emission economy on the exact same gas.
The journey of this element is essentially the history of the universe itself.
It really is. So as we wrap up this deep dive, what is the ultimate takeaway for you? What is the thought you want to leave resonating with everyone listening?
I think the most provocative thread for you to untangle on your own is this: hydrogen is the universe's most ancient, fundamental building block. It drove the evolution of the cosmos, the formation of stars, and the emergence of biology. And now, humanity is facing a climate crisis threatening our very existence. Could it be that our ability to finally master this incredibly simple, volatile element to safely and economically harness the primal spark of the universe right here on Earth is the ultimate technological test for our long-term survival as a civilization?
Wow, that is a profound thought to leave you with. If we want our civilization to keep evolving, we have to engineer a way to master the very first piece of the puzzle. Thank you for joining us on this deep dive into element number 1. We hope you keep looking at the simple, everyday building blocks of your world with endless curiosity. And hey, if you want to continue this journey through the fundamental pieces of our universe, make sure you follow and subscribe to Atomic 118 for more deep dives into every single element on the periodic table. Share the show with your fellow science enthusiasts, leave a review, and we will see you next time.